Hello, Umaya. This is the perpendicularity worksheet, and the first problem asks for a plot of a plane perpendicular to a vector and passing through a point. So I have used the code that was given and have made some modifications to get you a point. So that is the point, and the vector that was given is this guy right here. Did they call it vector or line? They called it vector, right? So the vector that was given is this vector here. The point that was given is this point here. And the plane that they asked for is this plane right here. This yellow thing, this orange-brown thing. That's the plane that they asked for. And then they asked for the equation of the plane, and here it is. This is the equation of the plane. They want it in XYZ form. So you would have to multiply this whole thing by 4 to get rid of the 1/4. And then just rearrange things using algebra to get something where you have something x plus something y plus something z equals something. Just to give you a full service treatment here, maybe I should do that. It will only take a moment. All right. Where was the Mathematica page? Here it is. Mathematica page right here. All right. Just to give you the full service treatment, let me just take a moment to convert this z equals 1/4 negative 2 minus 2x minus 3y. So now it's going to be 4z equals negative 2 minus 2x minus 3y. And I'm going to move the x's and the y's over here, so it's going to be 2x plus 3y plus 4z equals negative 2. So that would be the XYZ form of the equation, I think. Now, the MATLAB, the Mathematica code here is just the same as what they gave, except I don't have access to the axes 3D function, and so instead of using the axes 3D function, I have just used these 3 statements in there in the show function, and I don't have access to the viewpoint CMView parameter. So I'm sending you this notebook file. You can just adjust this to the viewpoint that you want to see, you know. This is really cool. Okay. And a helpful comment for you when you take your quizzes and tests is that the equation of a plane is very easy to make. It is just, you just have to get the normal of the plane, which would be the vector that is perpendicular to the plane, and that was even given. It was given as 2, 3, 4. And then you have to get a point, and that was also given. So once you have a point and you have the normal, you just follow the formula for the equation of a plane. And the formula appears again in a problem after this, so we will see it soon. And now BI. BI was asking for, G1 BI was asking for pick a point, and then add the 2 vectors running from this point to the other points. So add those vectors together and then use the result to plot a plane on which all 3 points reside. So we need a plane that contains all 3 points. So they've given us 3 points here, point 1, point 2, point 3, and we need a plane that has all those points. Okay, so here's how I've exercised that. So I've made a vector out of point 2 minus point 1, so a vector going from point 1 to point 2, and then a vector going from point 1 to point 3, so 1 to 2 and 1 to 3. So I've got 2 vectors there, right? And here are the 2 vectors. One of them ends with point 1, which is the green point, and one of them ends with point 2, which is the blue point. Right? So those are 2 vectors. The red point is point 1. Oh, I'm sorry. So the red point is point 1. So one of these vectors ends with point 2, which is the green point, and the other vector ends with point 3, which is the blue point. All right. And then I have made a plane that contains those 2 vectors, and I've made that plane by using the normal to these 2 vectors. Now, the way you find the normal, you probably already know from other homework, is you take the cross product of 2 vectors. When you take the cross product of 2 vectors, that will give you a vector that is perpendicular to both of those two vectors. So that will be the normal to the plane. Now, if your professor likes you to have the normal actually normalized, so the normal is a unit vector, then you're going to have to change this. You're going to have to divide this by the magnitude of itself, and that will make it a real normal, meaning it would be a unit vector that is a normal. Nowhere in this worksheet did they ask for a unit normal, so I have not normalized any of those normals. I don't think you have to, but just in case your professor has said otherwise, that is what you do. You divide the vector by its. So you divide the whole vector by its magnitude, its own magnitude, which would be the x squared plus y squared plus z squared and the square root of the whole thing. The square root of x squared plus y squared plus z squared of the vector. And so I have confirmed the work by showing the 3 points on the plane plot. So here are the 3 points on the plane plot. The blue point, point number 3, does not appear on the plane because I need to stretch the plane further in the negative y direction. So let me just do that now. The negative y. So this is the x range, this is the y range, and this is the z range. I'm going to stretch the point further in the negative y direction. So I'm hoping that this will stretch the plane. Oh, actually, that was the whole plot. I needed to stretch the y plane. So this y plane. So this is the plane. The plane takes it from negative x. The x goes from negative 8 to 5, and the y only goes from negative 2 to 10. That's not what we want. We want the y to be more negative x. All right. So there we go. So now the y is almost at the blue point. I'm still not at the blue point. In order to capture the blue point, I'm going to need to go deeper on the negative x. All right. So I'm going to have to go beyond negative 10 on the negative x. So let me make this negative 12 and make this also negative 12. So what I'm changing here is the range for the plane. I'm stretching the plane out. What I'm changing here is the range for the total plot. Right? So the plane is just a piece of this total plot. Now I want to stretch both the actually I don't think I need to stretch the total plot. I will just stretch the plane, and let's see if that's good enough. Right? So I have stretched the plane. I think the total plot is fine because it does include the blue dot. There it is. Yes. So now we have all 3 dots, the red, the blue, and the green, on the plane. You know, the green dot is a little obscured. So I'm going to stretch the total plot further in the positive x or perhaps the positive z direction. Positive z goes to 8. Positive x only goes to 5, so let me take it to 8. Does the plane itself go to 8 on the x? No, it does not, so let me make that 8. Okay. That didn't really help me that much. I still need some more on this plot in the positive x. Is this the x-axis? Is this guy the x-axis? Yeah, that's the x-axis. Positive x. Maybe I need, so this is 2, 3, 4, 5, 6, 7, 8. Maybe I need some more on the z. Yeah, I think I need some more z. So I'm going to add some to the z there and see if that helps. Ah, that does help. Okay, so yes, now we have them all. All 3 points are on the plane. I have stretched the plane to include all 3 points. That's great. And this is the normal. It's not a unit normal, it's just a normal. Great. Now, G1BII. At what point do these lines intersect? Plot the plane on which both of these lines reside and confirm your work by showing the lines and the plane in the same plot. Okay. They just ask at what point do these lines intersect. There is a way to calculate the point at which the lines intersect. However, they didn't ask to use that. I assume that in your other homework you have used that method. But this is Mathematica. So in Mathematica, I can just look at the graph if I want to. So that's what I have done here. I have just looked at the graph. And what was the question again? The question was, at what point do these lines intersect? All right, so here, let me remove the plane. Just temporarily. I'll put it back later. Okay, so I have made the two lines. So the line 1 is the dashed blue line, and line 2 is the solid blue line. All right, so I have made the two lines, and then I guessed where they intersect. I guessed with this point. The way I guessed was I just looked at this plot and I just oriented it in a way that is familiar and convenient for me, and I said, well, this looks like the x is 0. Actually, maybe the x is 1, so the x seems to be 1 there, and the y seems to be 2. Y seems to be 2 here, and the z seems to be 1. So I guessed 1, 2, 1. That was a guess. This was actually my second guess. My first guess was not correct, and let me see if I still have that point here. Point try 1, point try 2, draw point. Yes. So my first guess was 1, 1, 1, right? But that was wrong. I can show you how that was wrong. Draw point try 1, draw point try 1, draw point try 1. Okay, so that was my first guess, that point right there. And that was wrong, because that is not where the dashed line and the solid blue line intersect. Definitely not. So that was wrong. You know, I have made the points fat on purpose so that they're easy to see even when the plane is there. If you don't like how fat they are, the way you change that is by going to where I have draw point try 1 and draw point try 2, and then this last number, this is the fatness. So you can do that, and then you'll get a skinnier point. All right. I prefer to keep it fat though. All right. I'm going to pause this video because somebody's calling me over there. Okay, I am back. And they asked for a plane to cut. What did they ask for? They asked for so that's the point where they intersect, and then they asked to plot a plane where both these lines reside. So the plane has to be to take up the same space as the blue line and the dashed blue line. All right. So to do that, I made a vector on the blue line, and I made a vector on the dashed blue line also. So those are the two vectors. The way I made the vector was I picked 2 points on the line. So one point would be this green point, of course. It's on both lines. And another point I just picked at random. The way I picked a point at random was I had Mathematica do it for me. So there is an equation for line 1, and there's an equation for line 2. And these are parametric equations. So I can pick any point on line 1 by substituting t with any number. And I picked 5. Did I pick 5? Yeah, I picked 5, just at random, because I have 5 fingers. So that gave me a point. Now I subtracted from that the 1, 2, 1 point, the intersection point, which was my second try, the green point, and that gave me a vector. Mathematica thinks of a point and a vector in the same way with the curly braces, just 3 coordinates in a curly brace. So Mathematica would think of this as a point, but it would also think of it as a vector, depending on the context. All right, so that's how I got the 2 vectors, and I needed those 2 vectors because I needed to take the cross product of them. Why? Because the equation of a line is made of a point on the line and the normal to the line. And the normal to the line, a point on the plane and the normal to the plane. And the normal to the plane is made from the cross products of 2 vectors, any 2 vectors on the plane. And that's what I've got here. I've got 2 vectors on the plane. So I take the cross product of them. The way you take the cross product is with the function called cross. And then that allowed me to get a plane. I just plugged the coordinates of the normal and the point on the plane, which is this green point, into the formula for the equation of a line, and I got this plane. And you see this plane includes both lines, and it includes the point, of course. I think there was something tricky about this this plane. There's nothing tricky about this plane on regular paper and pencil homework, but there is something tricky about this plane on Mathematica, and that's because this plane is a plane that does not cross the z-axis. You see? This is the z-axis right here. Let me show you that it is the z-axis by scrolling down. Yeah, you see this z-axis? This plane does not cross the z-axis. So that means the coefficient for that. Let me show you the equation of this. The equation of a plane. So the equation of a plane, the equation of a plane, the equation of a plane. I think I typed it here for you somewhere. Well, no matter. I found it. Equation of a plane. Yes. Okay. So this is the generic equation for the equation of a plane. So XYZ form is this, and this is point normal form. I think you guys call this the point normal form, where the normal vector is A, B, C, or any multiple of the normal vector. It doesn't matter. And then the point that is on the plane is x0, y0, z0, right? Now, for this particular plane, in this particular problem, c equals 0, because there is no crossing of the z-axis for this plane. But that is a problem on Mathematica. And the reason is the formula for a plane to be plotted on Mathematica is... let me go back to the previous problem to show you that. Well, actually, I have it in a comment in this problem. So this was BII that we were doing, right? Yes, BII. Okay, so the formula according to Mathematica for Mathematica is this. This is how you plot a plane. So f of x, y, that would be z. So Mathematica thinks this is z. So z equals blah blah blah. So that means you have to solve this equation for z. The problem with that is that if c equals 0, then there is no z, because 0 times anything is 0, so there is no z here. This equation has no z at all, because c equals 0. So you cannot really solve this for z. If you tried to solve this for z, you would have to divide everything by c, but c equals 0, and you will get a division by 0 error. And so on Mathematica, you cannot use the usual way to plot this plane. You have to do a parametric plot where you tell Mathematica to pick any x, and you tell it to pick any z. And then you solve this equation for y, all right? You solve this equation for y, and then you give it the formula that you solve for, so y equals whatever you found y equal to, all right? And that goes in here. So you see, so you forget about z, right? So because c equals 0, there is no z. There is no z in this equation for this particular plane. There is no z. So then you solve the remaining equation, a blah blah blah, b blah 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 equals 0. You solve that for y, and y is going to equal something. In this case, y ends up equaling 1 plus x. So you put the formula that you just found for y equals 1 plus x, in here for the y coordinate of the parametric plot. So it's x, comma, whatever you found for y, not the letter y, but whatever you found for y equals blah blah blah, comma, z. That's what this is. I called my x any x, and I called my z any z. I know what you're thinking. Umaya, you're thinking, could I solve it for x and put whatever x was here and then put any y here? Yes, you could totally do that. If you wanted to solve this equation for x instead, that's totally fine. You just put whatever x equals blah blah blah, you put the blah 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 right here, and then you put any y here, and you put any z here. And then this function parametric plot 3D, it requires you to put the range. So any x, I want to go from -5 to 5. Any z, I want to go from -5 to 5. All right, I'm going to pause for a moment here. Okay, so that is how you have to plot this particular plane on Mathematica. You got to use the parametric plot. And then the rest of it is just the same as the previous problem. So we call this parametric plot plane, and then we ask the show function to show the plane, along with all this other stuff, line 1, line 2, point 2. This is the intersection point, my second try, right, the green one. And then both vectors. And also the normal. I guess you don't have to draw the normal. If you don't want the normal to be there, you can just delete that and then press Shift Enter, and then you'll have the plane without the normal. I like to draw the normal, though, because I think it looks cool. I forgot what it was called. Oh, draw normal. All right, yeah. I think the normal looks cool. All right. So, CI, G1CI. Okay, baby?
Yeah.
Oh, okay, good.
G1CI. G1CI.
So they want you to intersect these and give a parametric formula. Okay, so I have that in here for you, G1CI. I copied the problem this time. And then I gave you several comments in here, which will help you. So since I'm here, let me just explain these comments. So this is the final answer. If we call the parametric formula for the line of intersection R, this is what R equals. This is the parametric formula. Now, if your professor requires you to write this in the form of 3 separate equations, like x equals negative 4/3 plus 5t, y equals 7/3 minus 2t, z equals 3t, you can do that. Or you can just leave it like this if your professor doesn't mind. Now, I want to show you this graph because it's hard to understand. There's a lot going on here. The pink plane is one of the planes. The brown plane is one of the planes. The colors change on the underside. But what's interesting is this dashed line. This dashed line is the line of intersection. It is R. R is the dashed line. Okay? And let me show you how this was done. I have it in the comments here. So first, we had to get a normal of each plane. All right? So to get the normal for plane 1, well, the normal is easy if you use the, where was that thing? The equation, the generic XYZ equation of the plane. There it is. Normal is ABC. And that is convenient because that's what they gave us. They gave us 2 planes with generic XYZ equations. So the normal for plane 1 is just the coefficients there. Plane 2, just the coefficients there. And then we want a point on each plane. So to get this point, I converted this XYZ format into this point normal format, all right? And you could have gotten many different points. You could have subtracted 1 on both sides to get 0. So you need to get 0 in this point normal form. You could have subtracted 1 on both sides and put it next to z. Or you could have put the 1 next to the y. Or you could have put the 1 next to the x. Those 3 methods would give you 3 different answers. But any of those 3 points would be valid because they would be on the plane. So I chose to put the 1 next to z. So I put negative 1 on both sides. So that makes 0 on the right hand side and z minus 1 on the left hand side. But this the point normal form doesn't have a minus sign here. It has a plus sign here. So you have to put a plus here, and then negative 1 times the quantity of z plus 1. I mean z minus 1. I mean z plus 1. Yeah, z plus 1. So then that would give you a negative 1. That would give you a negative 1 here. So you can try that for yourself, and you will see how I did that. I did the same thing for plane number 2. Subtracted a 6 on both sides. Now obviously I chose to put the 6 on the x. And the reason why I chose to put the 6 on the x is because it would have been harder to put the 6 here or here, because here they have a non-1 coefficient. Here they just have a negative. It's easy to flip the sign so that this is negative 6 here. But if I had tried to put the 6 next to the z or to the y, I would have had to multiply the 6 by 3 or 2, which I didn't want to do. Alright, so that's how I got the points on the plane. And then to ask Mathematica to draw the 2 planes, I needed to follow the usual Mathematica formula for drawing a plane, and that is just solving the point normal, or that's just solving the XYZ form of the plane for z. You solve for z, and everything ends up getting divided by c. All right, so I did that for plane 1, did that for plane 2, and then here is me plotting the plane. Right, so this is the plane that I've just defined, and I want to use any x from negative 5 to 5 and any y from negative 5 to 5, and I plotted that as light blue, and plotted the other plane as pink. Right, these semicolons just mean don't do it yet, don't show me the answer yet. And then at the very end, when I put everything together, I used a show function to show plane 1 and plane 2. Now I want Mathematica to show me the answer. And then, excuse me, I have to cough. Excuse me. Now, to get the line of intersection of the two planes, I used a point on that line plus t times the vector cross products of the normals of the two planes. All right, so that's kind of a mouthful. Let me show you what I mean by that. So the line of intersection of these two planes contains the vector cross product of the normals of the two planes. And here's why. So, wait, let me pause this video because somebody's calling me. Okay, so if you get the normal of this vector, of this plane, of this, actually, it's not supposed to be brown and pink. It's supposed to be blue and pink. So let me orient this. It doesn't really matter, I suppose. So I just want to make this right side up. It was upside down before. Okay, so there it is. So now it's right side up. And yes, this is how it's supposed to be. Blue and pink, something like that. Okay, so anyways, if I take the normal of this pink plane, that's a vector perpendicular to the pink plane. If I take the normal to the blue plane, that's a vector perpendicular to the blue plane. If I take the cross product of those two normals, then I'm going to get a vector that is perpendicular to both of them. But the vector that's perpendicular to both of them would be a vector that could be on the line that of intersection for these two planes. So that vector could be on this line. Now, to make this line, I just have to add a point on this line to the vector that could be on this line. By adding a point on this line to that vector, I get the line, or I get a vector that is actually on the line, right? I don't have to add it. I could subtract it. You could add it or subtract it. Add the vector or subtract the vector to or from a point on this line, and you'll be fine. Now, how do I get a point on the line? Well, to get a point on the line, we just have to solve the two equations together. So solve the two plane equations together. Well, you can't do that because there are 3 variables and only 2 equations. So we just get rid of one of the variables. How do you get rid of one of them? Well, you just assume that z is going to equal 0 someday. Or you could assume that x is going to equal 0 at some time. Or if it doesn't work, you can assume that y is going to equal to 0 at some time. Or if it doesn't work, you can assume that z is going to equal to 1 at some time. So what I'm saying is you just pick something to eliminate. So I picked z. So let's see if it works. Let's see if I get a reasonable answer that doesn't break any rules of math when I set z equal to 1. And in fact, I do. I mean, I set z equal to 0. So if I set z equal to 0, then the z disappears, and I get this. And then I can add them together, and the x minus x is 0, and then I get this. And then if I solve for y, I get this. And if I plug this back into one of these equations, I can solve for x, and I get this. And these are all reasonable things that don't break any rules of math. So apparently, z does equal 0 at some point on this line. So great. This is a point on the line. Is this the only point? No. I mean, you could have guessed z equals 1, and then you would have eliminated z, and then you would have found a different point. Any point is fine. So this is a point on the line, and to get the equation of the line, I add the point of the line plus the normal cross normal, that vector that could be on the line. When I add that vector to the line, well, then that vector is on the line. I mean, when I add that vector to the point on the line, then the vector is on the line, and this t parameter means anything, any number here. So if I multiply that vector times any number and then add it to the point on the line, well, I have just defined the line completely, because t could be 0, t could be 1, t could be -1, t could be -1/2, anything you want, that will define all of the points on the line, which is the line. So that's my parametric equation for the line. I call it R later. And then to plot it, I use the parametric 3D plot again, this function again, where I use the parametric equation that I just made, and then I define what I want t to be, anything from -5 to 5, and this plot points, this I got from your worksheet. Plot points, I think it just means use this number of points to define the line. Well, you could use any number here. I mean, I've tried it with 15, but 2 is all you need for a line, though, by definition, right? Line, 2 points, that's all you need. And then I wanted to stand out, so I made it black and dashed. So that is how you do it. And then the next problem, CII, how can you tell without plotting that these guys cut each other at right angles? Well, whenever someone says right angles, and we're talking about 3D, you think of dot product, because a dot product of two things, two vectors that are at right angles to each other is 0, right? So it's hard to take the dot product of two planes because the planes aren't vectors. But every plane has a normal, right? A normal vector. So if we got the normal vector of each plane, if the planes are perpendicular to each other, then the normals of the planes are also perpendicular to each other. You know? Just try to imagine that. It's I don't think I plotted it for you. I didn't plot it for you. But you can imagine that. So if these two... Here, let me get something where there actually was a... Okay, never mind. So if these two planes were perpendicular to each other, then the normal vector, which is perpendicular to each plane, their normals would also be perpendicular to each other. So if I were to draw the normal to this blue one and draw the normal to this pink one, you see they wouldn't be perpendicular, meaning these planes are not perpendicular. But if they were perpendicular, the normals would be perpendicular. So I easily get the normal from this xyz form of the equation and the normal from this xyz form of the equation, and I've defined them right here for Mathematica to use. And then I took the dot product of them by using the dot function, and then I said this statement, and there they are. They do equal 0. Therefore, the planes are perpendicular to each other. Didn't have to plot it. Then the next question is, when you take all the lines which are also perpendicular, so all lines through this, which are also perpendicular to some given vector, what do you get? So the theoretical answer to this is you just get one line, right? But to show this in Mathematica, I decided to have you or whoever is checking your program input their own vector to show that it works with any vector. So the problem said vector ABC. So let me show you. We're going to define any ABC. So let's say A is 1, B is 2, and C is 3. For any vector like that, right? So this black thing is the vector that I just defined, that I just entered, and this red thing is the point that was given the problem. They asked for point 3, negative 4, 7, right? So point 3, negative 4, 7 is on a line that is perpendicular to this vector. But you see, this is the only line that's perpendicular to this vector that goes to this point. No matter how you turn this, there's no other way to get a line that's perpendicular to this vector, but that also passes through the red point, except for this dashed line. So what you get is a line. That's all you get. Just one line. That's it. Nothing else. No plane, no other pretty shape, just a line. That's all you get. So I want to show you how I did this. Actually, I want to show you I want to show you another vector. So let me do negative 5 and maybe negative 7 and then negative 1. Or maybe just positive 1. How about that? That vector. So there we go. That vector is different. It goes in the negative, in the negative x and the negative y, but positive z. Is that positive? A little bit of a positive z there. But you see, even with that vector, there's only one line that goes through the red point and that's also perpendicular to that vector. So the way I did this was I used their point for I used their point, and then let me pause the video for a second here. Okay, so I'm back, but I forgot where I left off here. I was talking about a line and a point. I think I was showing you how I made it. Yes. So this is the point that was given. So this is on the line that they're asking for, and this here, this is the equation of a plane. How come there's no plane here? I think I wanted to put a plane. Oh no. This is not part of the problem. Sorry. They don't ask for a plane here, so this is not part of the problem. The problem is the lines plot. Where is the line? The lines. Here it is. So This is the line. This is the equation of the line. This is a parametric equation of the line. So the point is the point that they gave. And then this is the parameter t. And this is a quantity that I got by using the dot product. Right? Let me show you how I got that. You might get a different vector here, but this vector is valid, and there are many vectors that are valid here because this number, this t, can be anything you want. But this is one of them that's valid, and let me show you how I got that. So the way I got that was I did the dot product. Let me clean this up and show you what I did. This is called color paint. All right. Oh, I need a new one. All right. And then make this black, and then make this big. Okay, so here's how I did it. So they want the all the lines that are going to be perpendicular to a given vector, ABC, right? And so that means vector A, B, C dot a bunch of lines needs to equal 0. So any line where it is dot this equals 0 would be valid. But actually not any line, only the lines that go through a certain point. So the vector on this side of the dot product has to go through this point, 3, negative 4, 7, right? Now that it has to go through this point. So if it's going to be a line that goes through this point, then it should be I can define that line with this point plus t times some coordinates that I don't know yet. So I need to know what these coordinates are. So I need to solve this equation for x, y, and z. Now it shouldn't matter what the a, b, and c is. So I'm just going to let a, b, and c be whatever they want to be. And let me show you why. So when you do the dot product, right, you take that. So if you have x, y, z dot x, y, z, right, then the dot product is x this times this, so x times x, plus this times this, so y times y, plus z times z, right? And we're saying that this is supposed to equal 0, right? Right. So let's do that then. So the x coordinate of this vector is going to be 3 plus tx. The y coordinate of this vector is going to be negative 4 plus y, ty. And the z coordinate of this whole vector is going to be z plus tz. 7 plus tz, right? Right now, so this is a vector. So this vector dot a, b, c needs to equal 0, right? So that means a times 3 plus tx plus b times negative 4 plus ty plus c times 7 plus tz equals 0, right? That's the definition of dot product. But this is one equation with a whole bunch of unknowns. It's impossible to solve this. So I'm going to again just think of an easy case where I could get not a general answer, but just one possible answer, because that's all I need. One possible answer. So one possible answer is if this is 0, and this is 0, and this is 0. This doesn't have to be the one possible answer that you pick, 0, 0, 0. This is just the easiest one that I could think of. You could pick anything, you know. You could have picked this is negative 1, this is positive 1, and this is 0. They add up to 0. Negative 1 plus 0 adds up to 0. Or you could say this is negative 4, and this is negative 4, and this is 0. Or you could say this is 4, and this is negative 2, and this is also negative 2. They add up to 0. So anything you want that would add up to 0, you could pick, right? But I picked zeros for each coordinate because it's just easy. Because then I would say A, 3 plus tx equals 0. And then I would say B, negative 4 plus ty equals 0. And then I would say C, 7 plus tz equals 0. But you see, it's really convenient that I picked zeros here, because if I divide both sides by A, I'm still going to get 3 plus tx equals 0. That's really nice. So it doesn't matter what A is. It doesn't matter what B is. It doesn't matter what Z is. It just doesn't matter, which is really nice. And then I can just solve x for t, right? Oh, actually, I can't because t has to be the same thing for all these guys. So let me just pick a t. So again, you shouldn't pick 0 here, because if you picked 0, then you have 3 equals 0. That breaks a rule of math, namely that 3 does not equal 0. So pick something else, not 0. So let's say that t equals 1. I feel like that's the easiest way. I mean, you could have said t equals 4, 40, whatever you wanted. But I'm going to say t equals 1. So if t equals 1, that has to be true for all these guys. So that means 3 plus x equals 0. That means negative 4 plus y equals 0. That means 7 plus z equals 0. So now I have made this huge assumption that t equals 1. I have made this huge assumption that 0 plus 0 plus 0 is going to get me a dot product of 0, right? So with all these assumptions, I get x equals negative 3, y equals 4, and z equals negative 7. I have not broken any rules of math. Now, interestingly, this negative 3, 4, negative 7 is equal to negative 1 times the original point. I mean, I'm not sure if that's a general rule that you've learned elsewhere in this class, but if it is, you don't have to do all this rigmarole. You can just multiply the whole original point by negative 1. But anyways, this is a valid vector for this problem. And so I use it. So here it is. Here's me using it. So this is negative 3, 4, negative 7. And multiplying it by any real number t, that makes, and adding it to the point that they specified, that makes this equation general for any point on the line, meaning it defines the line. So now I plot the line with the parametric plot 3D function. I give a range negative 5 to 5. You could give whatever range you want. If you want the line to look longer, you can make it negative 10 to 10, whatever you like. And you could use whatever numbers. You have to use at least 2 here, but anything more than 2 is fine also. And I made it dashed so we could notice it. All right, so here it is. It's dashed. Why is it washed out? Let's see. Oh yes. So let me do 3, 3, 3, and there it is. It's a dashed line. Okay. So that is how you do that problem. The input function is how I got the dialog box to show up on Mathematica. All right. So I said a equals this. I'm not sure if I needed to say a here, but just in case I did, I put it there. I forgot whether Mathematica requires you to put the variable here. I mean, since you already put it here, maybe you don't have to put it back there. But anyways, it works this way, so I just left it that way. Thank you. Bye.